This is my personal research net page and SSRN. If you go in there, I guess for this one, you have my papers as well as some presentation, not all, okay, that I archive. This will give you an idea of sort of interest that I'm in. So if you want to say come to me for projects, then I'll talk to you through some of them. But for example, if you go in here, there'll be something about copula modeling. That's something that has some open question that we can do projects in. The YouTube playlist is a little bit of what I did on the various topics like sustainability, as well as quantitative analytics. This is my personal playlist. I have a large playlist of many things, but this one is sort of like driven on AI data science. So those are good links. Okay. Syllabus, you have the PDF already. The notebook, I'll show you a little bit. Remind me to show you the notebook. Okay. Introduction to Big Data, Data Science, that's the EggMind. Yeah, we already have that. The learning journey. So now the last half an hour or so, I want to show you guys a bit about what Mathematica is all about. This year I want you to do. We did that already. The line group, the project group. So first of all, did you guys have something concrete? Like anybody ready to say, okay, we are the 7. We are ready to go. Anybody? You were supposed to do that. That was my coffee break, not your break. Okay. Tentative. Okay. Let's say you have three or 4 of you that are definitely going to be the same team. Anything? Okay. Group of 3 that already said yes to each other. Have you committed to? Doesn't have to be completed. Okay, any group? No group? Okay, we have a group of 2. Good. 2. That's it? 5. Okay, go stand over there. Go. Put on your mask. Okay, we have a group. That's it. Only 2 more spots, and this one is a done deal. Okay. Any of you dropping off the class? No. Feel free to drop the class. What am I doing? Someone over there. If you're thinking about dropping, I think you're dropping. Okay. Right. Let me give you a little something. Don't be afraid that you don't have to have mathematical background or you didn't do so well in the last year's Python program. Okay. It's not what you came with that is the limiting factor. The limiting factor is what you want to do going forward. Because I guarantee you, if you got A on the last programming class, or if you done statistics, you're going to learn new things. So consider yourself on equal footing. Okay? I'm not going to give you something that's so trivial that some of you would have learned in high school. So if you haven't got the background, that's not the point. Okay? But if you're not willing to dig in, that is the point. Okay? So if you have the guts to you have the stomach to go for it, that's good enough for me. Okay? That's the deal. Okay, so we got one group. Anybody else? Anybody else? The seeds, the seeds. I'm just looking for the seeds. No? Seeds? Oh, you got me, right? Okay. You did that. Okay, so we got 3, 4. Okay, that's it? 4. Anybody coming over here? Okay, so based on this assumption, at least we have 2 groups. Okay. Fine, go back to see. What about the other class? Let me. Nothing to do me. But again, I'm going to send my TA to the other class. Yeah. Yeah. Okay, we have Ken's group. You guys. Sanya. Okay, Sanya and Ken. You got this before. Good. Let me tell you something. I have seen people who are very good in math. I'm not one of them. That's why I'm not a professional mathematician. I love it. Yes, I love mathematics. And I read a lot. But I don't have the raw talent to be a professional mathematician. Okay? That's why I work in business. In fact, when I go to university, when I recruit mathematicians, I always tell them, if you're the best in the class, don't come to me. I only want the 3rd, 4th best. Okay? The top 3, maybe 4th, the 5th. I want them. I don't want the best, because the best, they better use their mental capital elsewhere. Business problems are not that difficult. Okay? I make them difficult because I try to explore the region of the problem that's not addressed by traditional method and try to create a generalized approach from it. To be honest, there's no rocket science. Okay? There's no rocket science. Right. So let's have some fun looking at some mathematics. Now, before I started the consultancy project, we were down with COVID, right? You guys remember that? Well, it's still with us. So what I did was created a little application in, where are we? Well, I'll just show you. Okay, I'll just show you. All right, pedagogical. Right. So this is my little COVID analytics. Okay. There is a cloud version of it here. If you go to here, COVID analytics. Okay, I haven't put a lot of things up here, but if you go to my playlist here, there are, for those of you who are interested in the sustainability problem, I did some work with sufficiency economy modeling, such as here. This is sort of various lectures. I just put 2 of them because Now, the COVID analytics, you can look at the playlist.
Hello, everyone.
It's got 4 of them, 2 parts, one in English, one in Thai, so that's 4 videos. Explain the Mathematica foundation. This is my PyCon talk. Again, I told you that it's a Python conference, but the model that I presented was developed first in Mathematica. Okay, so go look at that. Now, the COVID analytics, it gives you the explanation here, but there's no microphone here, so I'm just going to show you the software. Right. So this is example of what Mathematica does. It embeds the computation within the document. You guys know about words, right? You have words, you have text, you have PDF, okay? Now, originally, those are all flat. Then you start to embed things like HTML. So you can go PDF document and click, and then you launch a web page, right? Right? You've done that, right? Okay? So likewise, this Mathematica works on what's called computational computable document format, meaning it can look like a PowerPoint, but instead of having just a PowerPoint, you can literally click into the computation and then just start a computation. For example, oops, sorry. Now, this is something that might look a little bit daunting, but I'll show you how simple it is. Okay, COVID, you have 4 populations. People who are infected, that's the I. People who are susceptible, who can be infected. People who have infected and recovered. And people who have become non-people who died. Okay, these are the 4 populations. Okay, as they grow, what happens is susceptible people get infected and then they recover or they die, depending on different rates. Now, this you would think that it's modeled mathematically as a probability distribution. No, it isn't. It's actually in Lambat epidemiology, the standard approach is to use differential equation. And basically, differential equation is like differential you learn in high school, but in a modeling sense. In other words, if you learn about y is equal to f of x, right? The rate of change of y with respect to x, that's df dx over f prime, that's differential equation. Okay, that's the rate of change. Yeah. So rate of change of position is speed. Rate of change of speed is acceleration. Simple as that. And that's the definition. But when you go to the real world, you have to relate this kind of analysis with the real world. For example, the rate of infection is proportional to what? What's the rate of infection? Proportional to number of infected people you have to begin with, right? Right? So in this class, you will think the rate of spread also depends on how many disease you start with. You start with 1 person, then you have to spread from here. But if you start with half the room, the next hour, everybody will be infected, right? Okay, so the rate of infection, that's the rate of change, that's calculus. But it is proportional to the number of original infection. So when you put calculus term, like rate of change, with real parameter, like the current number of infected people, you have to put them in terms of equation. This equation contains differential calculus terms, so it's called differential calculus. Now, because we have 4 populations, the rate of change of the infected, susceptible, death increases, you have 4 differential equations. Simple as that. Now, what's cool about Mathematica is once you model this, you just write that down in Mathematica. So this is what I did. Okay, this is literally what I did. Can you guys see it? Okay. F naught, that means originally, let's say you have 999,000 995 people not infected. IO, originally 5 people are infected, right? RO, initially recovered, nobody's infected yet, so nobody recovered, nobody's died. So that's the initial condition. So SIRD with 0 meaning initial condition. Equation simply say susceptible S prime is what? Is proportional to the number of susceptible people and the number of infected already. So that's the equation. Forget about the detail, but this is basically you translate English to mathematics. Okay? So like I told you earlier, you have 3 languages: mathematics, English, and programming. With mathematics and programming is very tight. So when you write something in mathematics, it already becomes a code. Okay? So that's it. 4 differential equations. I say, please solve them, then apply them. Okay? So this is, and that's it. Based on initial condition, you see that the line of the susceptible decrease. Okay? And some people will come infected, some people die. Now, the trick is the parameterization. So I put all of the above into a little box that say, well, let's play around. This is called manipulate, meaning I can manipulate the parameters. So these are like infection rate. So this is a different scenario. So literally, this is what I do. Okay? Based on certain parameter, you end up with 200,000 people dead. Based on certain parameter, you end up with even more dead or even less dead or something like that. So these are all different conversions. How much of a work do we have to do? Literally just 3 steps, right? First, find out what the epidemiologists, what do they call themselves? Well, the scientists, what they say about how disease spread. They say there's 4 populations. This population grow as a proportion of infected and so forth. You translate that into differential equation. You put in Mathematica, and then you say for this model there are 3 parameters like actual rate of infection. So just because you are in touch with someone, that doesn't mean you automatically become infected. So there's a good probability. So those are parameters. So parameters is right here. Okay, parameters right here. Now, so basically, let me show you that at the end, it looks like this, and there is if you click on this link, you actually have a live version you can play with. Now, it feeds off data that is a few months old. Okay, a few months old. If I want to rerun with the new data, I have to but this one is like a fraud. What happened is I wrote the application in Mathematica, then I put down a command, say cloud deploy. And this gives me a URL. What it does is it frees an instance of that program and I put it for anybody. I put it as public. So anybody can click this link and go to this, and it becomes online. So immediately in one line, I just cloud deploy my app. Okay. Now, once again, if you're going to do this on an industrial scale, you have to do it with Python because it has all the facility for life. But this is your internet, so it's going to take a bit. Okay, so go play with it at home. Basically, it looks like this. I made a little screenshot just to make sure that. So this is an outcome of a SID model on Thailand. Now, this was run on what? This was run, I think, this is a screenshot. May. Yeah, May. So let's see where we are. So this is based on the parameter. Now, in theory, you would fit parameter against data, but I hand fit the parameter. And this is what the model predicted would be the convergence. So Thailand should have 3,000-ish case, 54. In reality, the real number is different, right? It's 58. But it's pretty good. It's very good. It's very good because the mathematics is good and our behavior is predictable, right? Now, I try the same thing, okay? You can look at it for this application when it comes on. I try for the US data, okay? So I calibrated in early May and I based on the projection. What happened? Since May, America got a little bit antsy and opened up the country. So the second wave, in fact, the first wave hasn't gone yet. So the model is completely useless. Okay, so there, the model is only as stable as the dynamics you model. Okay, Thailand happened to be a very, very good example. In fact, we were the first country outside of China. So by right, we should know what we're doing. There was nothing to learn from. Okay, and all the countries on the media say, you know, Singapore is very good or South Korea is very good. Those guys came later and they are fucking much worse. We were the first case outside of China. And we probably did better than anybody. Okay, so in this case, it's very good. The model fits very well. Okay. Now, what it does is, again, based on this, let me show you just the picture. Okay. So this is evolution of total case and evolution of death. This is the actual number at that time, and this is the number that's fit by the model. That's the blue line. This is the error function. These are all the parameters. Okay. I adjust the parameter on the right-hand side here. And this is a projection into the future. Well, it's not future now, it's present now, but at that time it was future in May. So that's it, very simple. Okay. So you go to the playlist, the YouTube, there are 2 videos each language, one in English, one in Thai, but you know, I don't use any real script, so I cover slightly different. So that's Mathematica. Now let me show you another. Okay, this one. Okay, let me show you how simple it is. Because MNIST is like a handwriting database. Okay? It's a well-known database. So Mathematica store it as resource object. Okay? There's a catalog, there's a menu. Say, okay, the data is equal to this. So when I enter this, it goes to the internet, retrieves from the database. Now, this data also separate training data set from testing. If you don't know about it, we'll talk about the machine learning. Basically, you fit against training and then you test against the testing. So this one, take the resource data, take this part. So we call this training data, this test data. Now, this is called random sampling, meaning I take a sample of 5. So if I take 10, there'll be 10 of them, random. Okay, so the data set here contains the input. That's the handwritten recognition. That's like 29 by 29, I think, matrix pixel. So it's a pixel bitmap. And the right-hand side is the label, right? So a more advanced version would be picture of a person and the name of the person. Okay, but this is like a classical MNIST. This is what, when you look at my syllabus, there's a section called seminal paper. The paper that introduced convolutional neural network in 2012, I think it was based on this. Okay. So basically that's it. The machine is supposed to learn from this to that. Okay. Now, this is Mathematica's way of specifying neural network. Okay, it's extremely simple. When I was a student, you have to code everything in C. Back propagation layer by layer, it was very difficult. In fact, I didn't bother to do that. Okay. But this is it. This is what the model looks like. Okay. Now, this is the command to train. Now, this is going to take a long time because it's a big data set. So what I did was this instead. I said, okay. Net train, this is the model, this is the training, this is the testing data, this is like a parameter that say, you know, how much time you want to spend. This is targeting device, GPU. My laptop here is a gamer's computer, so it has got a GPU card. So this is twice as fast as that. So I go like this, boom. And now, yeah, it's gonna start running. Maybe it's getting gun shy. Why is it getting gun shy? Okay, this is the whole result. Supposed to take 15 seconds, but it'll download. Oh, have we downloaded already? Okay, it's starting already. So this is, but this is the learning error. Okay, it's automated. Now in Python, you have to build for example, go to a TensorFlow library, do a tensor board, do a mapping. I've done all that. It's just painful. So if you're not into the nitty-gritty of computer programming, mathematics is much simpler. It's more powerful, but it's also simpler because a lot of the routines have been packaged. Because they know that when you do machine learning, what do you want to do? You want to train. What do you want to do? You want to monitor the error surface. What do you want to do? You want to see the result. So because this is standard practice, they encapsulate this as one command. Okay? So it's much quicker to program just one line. But in terms of execution, it takes a bit longer because the back end is not C like Python. Python tends to be faster, I think. Maybe not. Okay? So that's it. So it's trained in 26 seconds. Okay, 26 seconds. The last output 15 seconds was my CPU at home. This is a cheaper CPU. You guys know about CPU computing, yes? Anybody playing game? Gamer? Okay. Why do I say that because you have MacBook, you're not very muscular computationally because you don't have CPU cards in Mac. It's not a platform for it. Whereas gamers, they use PC. They have a GPU card. Now, what's a GPU card? Well, a GPU means graphical processing unit. What's a CPU? Computing processing unit, right? They do the same thing. The difference is CPU does complicated computation one at a time, right? GPU does simple computation, a whole bunch of them simultaneously. Parallels. Why do gamers need that? Because when they draw a picture, right? When they draw a picture, let's say there's a picture of cup. This is coordinated in 3D space. So that's what? What's a coordinate in 3D space? It's a vector. If I'm going to move this, I relocate the cup. What happened? I move the vector. What's moving the vector is matrix multiplication. I haven't moved the vector, I haven't moved the cup, but I changed the view. Same thing. The projection is the moving. So I move the coordinate with respect to the view. So that's matrix multiplication. Matrix multiplication for this part of the screen is not affected by multiplication in that part of the screen. So what the GPU card does is separate the computation of the screen up there into tiny multiplication done separately, right? Well, when you learn about neural network, you will find out that a neural network does a lot of matrix multiplication. Okay, so data scientists like us and gamers, we actually buy the same piece of hardware. That's why I look really cool with this, this RGB colors and whatnot, but I don't play the games. Okay, right. So once you learn, then just do some prediction. Now the difference between this and before was from the database. This is from the model. So it inputs what looks like A and it gives a label A. That's it. This was the breakthrough in 2012. The combination of the neural network architecture, this thing here, okay, and the fact that the researcher used GPU from a gaming industry. Okay, I think it was NVIDIA before very primitive by today's standard. They use that and solve this and beats everybody. So go read about it. Go read about it. So this now is in the guy who did it in Python. So the code is obviously not wrong. There's what's called boilerplate code. Boilerplate means things that you use all the time, but every time you use it, you have to write it. So you copy paste, the whole bunch. Well, this gets you around. So if you're not very good with 2 reasons to buy Mathematica. Well, 3 reasons. 1, because I only got contacted about this class very late, so I didn't require it. For next year's class, I'm going to require it. Okay? Second reason to use Mathematica if you want to get to the advanced functionality. But the third, and that's probably the reason why you might want to get it, is because it's much easier to code. Okay? But for the project, chances are you have to do a little bit of what I did, which is prototyping and implementation. It may well end up being a Python code again. So that's why I wanted to have a good mix in the group. So maybe this guy is very good in Python coding, right? But it's not interested in problem formulation. And then you can do a little bit of division of labor, you formulate problem, prototyping Mathematica. You can do all kinds of stuff. But I advise that at this learning stage, try not to do division of labor at this point. There's a tendency to say, oh, you're good in programming, you do programming, and I'll do the presentation because I look nice. Try not to specialize at this stage. Okay, this is not the time to specialize. Good. What else? Now, Mathematica, I ask all of you, even if you're not going to buy the software, which costs money, you can download the player. Okay, a player means that once somebody writes a software, like I did, in Notebook, okay, I can export it as a flat, no, not flat, as a fixed computational document format. Then you can play it. You can play with the functionality, just like the cloud application. You just can't write it. Okay. Now, before I do a little bit of tour of Mathematica, well, you go follow the link. We're going to go over the time a little bit, but that's because we were wasting time in the beginning. So go through all the links, especially this page. This page is very interesting. I want to show you guys. This is an example of what's called the second element of big data. You don't have coordinate data, you have picture. You have picture, right? Picture is data. So this loads, okay? Once, I'm not gonna do computation live. This is a sort of screenshot. So you do this, you load the picture, right? You do some kind of binarize, meaning darken, right? So you get this outline. Now, here's what Python cannot do now from this on. It's gonna take forever to do, even in coding. Immediately, Mathematica treats this as a mathematical object. So all the lines here are like boundary condition. So I triangulate it. So I use what's called boundary mesh, triangulate mesh. It becomes a mathematical object right away.
Once it becomes a mathematical object, it's like a domain that you can compute. So now this is where the math gets tricky. This is where engineers can understand. This is basically, you know, divergent and curve. Never mind. It's a shorthand way of writing fancy differential equation. Okay, instead of writing 4 lines, you write just 1 line, but it contains a lot of information here, and blah 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 blah, and that's it. And based on that, you can literally simulate, okay, or calculate what happened when you drop, say, a meteorite. This is actual node of this lake. This is what would happen if you drop, and you can play with this. Oops, it's blocked for some reason. You can play live animation, like what happened when the meteorite dropped. There's a way of propagating. It hits the boundary, comes back, interact. So this is something that's not doable in Python. Now, the last thing I want to show, and I'll let you guys go, is what I originally intended, but I don't think we're going to have time, is that for the class, this is what I'm going to do. Write my own textbook, but in Mathematica. Okay, so that when you go to different section, when you go to, say, for example, linear algebra, right, and go to eigenvector class, you can play with it. This is basically what happened to, remember I told you that when you look at computer graphics, it's the image location that has to move. Well, that's like a vector field. It's like where you are tells you where you go next. That's what the vector field is. If you're over here, the arrow tells you where you go. So based on different function, it goes different points in different direction. So this is vector field, which is very difficult to do and visualize. But in Mathematica, just a couple of lines. Now, this, you'll notice, is written in kernel form, meaning if you learned Python last year in Jupyter, if you use Jupyter Notebook, you should have Jupyter Notebook. Okay, in Python, you should have learned Python using Jupyter Notebook. Jupyter Notebook actually copies the idea from Mathematica, not the other way around. So we have, so what I wanted to do is all the lecture is in here, but I don't guarantee that I'll have enough time to prepare for the class because this is very last minute kind of thing. Yeah, so what I might end up doing is just use the PDF scan of Excel compare books. So that's it. So I'm going to give you a little bit of homework. The homework is for you to go to Mathematica demo. That's this site. Okay. It's going to be something. Where are we? Right. So this is Mathematica demo. It's a little bit like what I did, except simpler, shorter, and downloadable. Meaning all you have to do is download the player, then you can do all the interactive. So these are little projects. These are little projects. Each one of you will do what I said. You know, go pick the one that you like to go into details. Now, the first week, I don't expect you to go through the code. I expect you to just download and play with the parameters and the insights in the problem. Now, we should have a system whereby if you look at this demo, you should look at the other people should look at the other one. So maybe in 9 or something, we have a way of saying, I'm looking at this link, don't look at this one, go to somewhere else. Is there a way to do that? Yeah, create a note or something like that, right? Okay, so by next week, I just want you to go download, play with it. It tells you what the inside, how it allows you to play with the parameter, and whether or not this gives you an idea for the project. Okay, that's it. That's your homework number 1. Okay,ครับ. Hopefully next week it won't be as hectic, and we get going on the core lecture, and try as much as you can to come up with the groups. Okay, that have to be all 7, 4, 5, and then we'll sort it out. Okay, ครับ. Good luck. สวัสดีครับ